So, Tyler is a research associate at the Institute for Defense Analysis, IDA, within the Science Systems and Sustainment Division. He holds a master's from the University of Chicago in chemistry and a bachelor's in physics and mathematics from Massachusetts Institute of Technology. In addition to his detection and classification scoring work at IDA, he works on model verification and validation, data analysis, statistical testing, and technology assessments. And his talk will be on addressing ambiguity in detection and classification tests.
Switches. Yeah. Hi, everyone. Thank you for the introduction, and thank you all for being here. So in my talk, we're going to discuss really some results that came out of IDA's attempts to score underwater unexploded ordnance detection and classification tests. And really, well, the methods developed here are focused on this application. The framework is presented so that way it can be applied to other types of tests where you rely on trying to pair detections with actual targets of interest. And the reason, and for any of you who are unfamiliar, unexploded ordnance are weapon delivery systems which did not explode when used, and as you can imagine, pose risk to public safety because they can explode at later times. You can see here an example of an unexploded ordnance found off the coast of Hawaii. That said, they also can be in the nearshore terrain, where they can pose more direct risks to the public. And this is not a contained issue. These are all over the US. So here's a map of formerly used defense sites, and many of them have UXO contamination. And only the green triangles represent sites that have already been fully remediated. So now that we know why this is an important problem, moving on to the technology that helps solve it. So detection and classification technology finds where objects are present and which are likely to be UXO. So detection answers the question, is there an object here? When classification tries to answer the question of what type of object it is. Is it a target of interest, which for our case is UXO, as you see on the left? Or is it clutter, some other object that you're not interested in? And then identification takes that one step further and answers whether or not it's a specific type of UXO. So, and the reason why classification is so important is because time, money, and resources will be spent in remediating. So if you think that there's something there and you send someone on the land side, for example, to dig it up and there's nothing there, that's a waste of resources. So you want to minimize that as much as possible. So here's an example from the land side, and it's a former Marine Corps base camp. And on the left, you see anything that they identified as a potential explosive risk. But on the right, you see what actually was an explosive risk. So it's 50,000 points versus less than 500 points. So you're going to save a lot of money if you only check the areas that you're actually the most concerned about. And to do that, you need to be able to classify. So these capabilities are essential to supporting the UXO remediation effort. And primarily, they play into the remedial investigation, where they aim to identify the nature and extent of the UXO contamination. So where things are and what's down there. And from the information they gather there, and detection classification results are key, they can assess the feasibility of different options and propose an action plan. And then from there, they move to the remedial action, where they enact the chosen action plan. And once again, they might use detection classification technology again if it's an energetic environment, so things were likely to move since the last time they measured it. Now, in order to understand the capabilities of these systems and the operational envelope for each, because a lot of them have different strengths and weaknesses in what they can cover, a strategic environmental research and development program and environmental security technology certification program are two DoD programs which fund detection classification tests in order to address these gaps. So they solicit proposals and select technologies and test locations. And IDA also supports this process in helping them review their proposals. And then the testbed manager will go ahead and emplace the objects down there, which are UXO surrogates. They're not putting live UXO down there, as you can see on the left. And then they measure exactly where that is. So you can see a diver holding a beacon up to the UXO. in order to geolocate the object. And then after this is done, the demonstrator comes and they use their technology to try to find where the UXO are. So you can see on the left, top left, a picture of them lowering their sensing array down to the water. And then on the right, an example of like a real-time visualization. But it's a lot more than that because they also have to dig into the data and not just, they can't just rely on live visualization. Anyways, and then, so the previous two send inputs to the program office, and then IDA gets it, and our job is to provide independent evaluation. So score the test results and also communicate it to the stakeholders. So this includes everyone shown here, but also regulators and managers of the formerly used defense sites all have a stake in understanding the capabilities of these systems. And a good example of this test is the 2022 Squim Bay blind test. So this test occurred from July to October 2022, and the test area was 7,833 square meters, which sounds like a lot, but it's this little dot in the wider Squim Bay. There were 2 different demonstrators who came that year, and each had access to the site to collect data for around 5 days. And then around 6 months later, the demonstrators had submitted all their lists for scoring. So focusing on the ground truth now, so the testbed manager side, they distilled the information that they collected into a ground truth list. And this has a unique identifier for each object, the geo coordinates, so where it is, whether it's TOI or clutter, and a description. And we can plot this data as shown on the right, and this is like a bird's eye view of the testbed. So the magenta line shows the test area, the red stars is the target of interest, TOI, and then the green circle is clutter. Now, moving our focus to the demonstrator side, they summarize their findings with a ranked detection list. And this list is a list of all the detections, and they've ordered it such that the ones that are at the top are the things they think are most likely to be a UXO, and the ones at the bottom most likely to be clutter. And they'll choose a cutoff, the demonstrator dig threshold, for above which everything they say is a UXO, and they think everything below that is a clutter object. So once again, we can plot this, and in the zoomed in region, we see the black diamonds are the dig decisions, which are the detections that they thought were a TOI, and do not dig decisions, which are detections they thought were clutter. And those are yellow. So in this case, it kind of looks like they did well. They found all the TOI in the zoomed in region, but we need to be able to quantify this in order to compare it to other tests. So we can do that by scoring. And scoring aims to quantify how well the dig decisions, which are, once again, the things that they think correspond to a TI, line up with the ground truth. So in this example, on the bottom left is an example of a true positive. So that's when you have a dig decision and there actually was a TOI there. By contrast, a false positive is when you have a dig decision, but there's not a TOI there. And then the third thing that you also care about is the number of false negatives. So that's when you have a TOI, but there was not a dig decision nearby. So this is something they should have been able to find, but didn't. And you can determine what's nearby based on the halo radius, which is just the maximum distance between a TOI and section in order to count as seen by it, essentially. So we represent this by a circle around the dig decision. So on the top, it counts as seen because it's within R. But on the bottom, it does not count as seen because it's outside of that halo radius. Halo radius is a choice, and your test results will depend on that choice. For these tests, IDA has been the one choosing the halo radius, but there's no one answer. And really, you should be making this decision based on what the technology is going to be used for. So for example, 10-meter halo radius is not feasible for this application because that's not a feasible area for a diver to cover in one dive. That said, if you're looking for a technology which has to deliver explosive, you might not care if it's 10 meters away. That might be more than sufficient. Now, all the cases that we've seen here are where you can directly pair a dig decision with a TOI, but that's not always the case. And actually, this comes up a lot for underwater UXO tests. And that's because of the large halo radius you need. So on land, the halo radius was just 25 centimeters, which is about half the width of a shovel. The idea is if you are standing at the spot and you dig straight down, you would find the object with your shovel. Meanwhile, for underwater, due to the difficulty in the environment and also the difficulty to geolocate precisely where things are, the halo radius typically needs to be 2 to 4 meters. And this ambiguity can occur either when there's a dig decision near multiple TOI and or when there's a TOI near multiple dig decisions. And trying to apply scoring methodologies to these ambiguous cases can become challenging pretty quickly when you get to more complicated clusters. So on the left, we have a case where there's 2 dig decisions and 1 TOI. And for our case, we count that as a true positive and a false positive because they found one thing. So it doesn't make sense to give them credit for finding a second thing. In the middle case, we have 2 TOI by only 1 detection. So in our case, we're deciding that this counts as 1 true positive and 1 false negative, with the idea that a diver might go down and they're told there's one thing there, they find one thing, and they might cease their search. So the second one might go unfound if you only say there's one thing there. But then it's very unclear how you'd go about trying to apply this simple cluster approach to the complicated cluster on the right. And the way that we've developed to do that is to formulate it as an optimization problem. And this process starts with deciding on what you're going to pair between dig decisions and TOI and whatever function you want to optimize. And then from there, you can write each allowed pairing for a cluster. So describing the structure of the cluster essentially as a matrix. And then from there, you can translate these into formal constraints and an objective function that you're trying to optimize. And in that point, you have an interior optimization problem, and you can use standard packages to resolve it. And the priorities of technology should inform the rules that you use to constrain the pairings and also what you're trying to optimize. So our rules for selecting pairings is that each dig decision and TOI can only be paired if they're within 1 halo radius of each other, as we talked about earlier. Also, each TOI can only pair with 1 dig decision. And lastly, each dig decision can only pair with 1 TOI. And then the function optimized here is the number of pairings, which is just the number of true positives, and we want to maximize that. So we can see on the right, there's 2 different example pairings between the TOI and dig decisions, and this is just the cluster we saw earlier, but without the circles so you can see it better. So we want to be able to determine, are either of these something that you should be using for scoring? We know that given we want to maximize that, we'd prefer the bottom one, but we want to investigate whether that's actually optimal. So moving on to the second part of describing the structure in matrix form. So you can do this with the matrix S, and that describes, for your given cluster, what TOI is near which dig decision. So the rows of this matrix correspond to the number of TOI, and each row corresponds to one specific TOI. And then the columns correspond to the number of dig decisions. Each column corresponds to a single dig decision. And it's 1 if the corresponding TOI and dig decision are near each other, and 0 otherwise. So to give a simple example, column vector 1, 1 corresponds to a case where you have a dig 1 near 2 TOI. Let's call them U1 and U2. And this is pretty simple and can be done for a complicated cluster. So moving on to how we're going to describe the pairings, and you can do that with the matrix X. So it's the same shape as S, and the same, rows and columns correspond to the same TOI and dig decision, but it's 1 if you're going to pair that dig decision and TOI, and 0 otherwise. So for the example we saw earlier, X can be 1, 0, 0, 1, or 0, 0. It can't be 1, 1, because we've already said that a dig decision can't pair with 2 TOI. And going back to those constraints, we can formalize them in matrix form with leveraging X and S. So the first one, that each TOI can only be paired if they're within R of each other, really corresponds to the case that if the S matrix, which describes what's nearby, says that two things are nearby, they should never be paired. And you can capture that by taking the trace of X, quantity, the identity matrix minus S transpose, and making sure that's equal to 0. And then for each QI only pairing with one dig decision, you can capture that by summing each row, and if it's at most 1, then you've satisfied that. And then for each dig decision pairing with only one TOI, you can sum each column, and that's at most 1, then you're good. And then the last constraint comes from the definition of X, that each entry at X has to either be 0 or 1. It can't be some other value. And optimization will tell you an optimal choice of your metric of interest and a representative set of pairings. So as I mentioned, the function optimize here is the number of true positives, and you can get that by just summing the X matrix. So in this case, the number of true positives for the top would be 4, and the bottom one would be 5. From doing the interior optimization, in fact, 5 is the best you can do, so you should use that for scoring. And to calculate the others, you can leverage the total number of dig decisions and TOI. So false positives is just the number of dig decisions minus the number of true positives, which is 1. And then false negatives is just the total number of TOI minus the number of true positives, which is also 1 in this case. Now, while this cluster by cluster approach is helpful for digging into complicated clusters, it's not as helpful for stakeholders who want the higher viewpoints. So to do that, you look at the receiver operating curve, or ROC curve, which summarizes detection and classification scoring by showing the balance of safety and unnecessary costs. So you can see here the x-axis is the number of false positives. That corresponds to an increasing cost. So that's a place that you checked that you didn't have to check. So, bigger is worse. Meanwhile, the y-axis, probability of detection and classification, which is just the ratio of true positives and number of TOI, corresponds to increasing safety. So you cleared out more of the area by checking those the detections, basically. And the demonstrator threshold is a point on this. So each point corresponds to a different choice of where to draw that line of what to consider a TOI. So this is not a very good ROC curve because it takes a lot of false positives and doesn't get that high in terms of finding everything. That said, by contrast, this is a really good ROC curve. So with 0 false positives, it hits the probability of detection and classification that the previous one does, and also with very few false positives, gets almost everything. So moving on to how we use what we were talking about earlier in order to calculate this. So you can calculate you can use the individual cluster scores for a given threshold to calculate a point on the ROC curve. So here's the example we saw earlier, but the one difference is that we changed the last 2 detections on the list to do not digs. So thinking there's clutter there. And in this case, there are 7 dig decisions left. 5 of them are true positives and 2 are false positives. And the 5 true positives correspond to TOI that you found, and the 2 false positives, unnecessary digs. But you also missed 4 TOI, which are false negatives. So the probability of detection classification is just 5 over 6 in this case, or around 0.56. So you can plot 2 and 0.56 to calculate that point on the ROC curve. And you can repeat this process for every threshold. For example, what we were seeing earlier with all of them being dig decisions corresponds to the 2 points up on the ROC curve relative to the blue dot. So in order to summarize, ambiguity has made it difficult to apply the standard detection classification scoring methodologies to provide consistent scoring to underwater UXO tests. And optimization has been successfully applied to consistently score and summarize these UXO tests. And although we only showed it for scoring here, it can also be used for other test summaries. And while the focus has been on these underwater UXO tests, really the goal here is to present a flexible framework where you can tune your function to optimize and your constraints to meet the test goals, to provide scoring and or summaries for whatever tests you have. Thank you all for listening.
Okay, we've got plenty of time for questions, so ask away.
Yeah, so I have two questions. One, is there a concern that you're over-biasing your true positives by optimizing for it?
Yeah, so I mean, this is really the low data limits. We don't have much data. So, I mean, it could always be the case, even if there's no ambiguity, it could be the case that there was a TOI nearby, but that's not what caused the dig decision, right? Especially if you have like a really small one that the system might not detect. If you see a detection near it, a dig decision near it, it might be the case that something else caused it. So, I mean, you have to make a decision somewhere. At least this way it's consistent and can be directly compared across tests.
Okay, and my second question has to do the example you gave. We have a dig decision, and there are two TOIs there, right? Do you, in the instructions given to the people making dig decisions, are they told do not try to be efficient? Like make separate dig decisions for each time you think there's one, or like, do you know anything about their training or instruction that you could actually then make that call and say that is also a false negative?
Yeah, so do you mean for lands or underwater?
Yeah, I mean for the actual underwater UXO tests, like so
Yeah,
if it's in the R and like someone just sees two things in front of them and they think they're both
yeah,
TIs,
so
like maybe they just say just dig here once.
the demonstrators, yes, or communicate that they should have one section for each dig decision. In terms of what divers will end up doing when this has progressed to the point that divers, are actually going down based on it,
Mhm.
it's unclear. But this is essentially the safer option of not assuming that they exhaustively search if they already found something.
Good question.
I just had a quick question about the rock curve. Like, is there really a value to having a rock curve since, like, I mean, this is an incremental counting method on the operator's end, but we're looking at the results in aggregate.
Yeah, so I mean, first of all, the rock curve tells you like how many things did they detect. So if you were to not care about classification and only look at detection, are they actually detecting everything? That said, also, it really shows the sensitivity to the choice of the demonstrator's decision of where to draw that line. So in some cases, it doesn't really matter too much. In other cases, if they went a little further, they might have actually found like the last one or something like that. So yeah, it's just a better understanding of the tests relative to just looking at essentially what specifically the demonstrators choose.
All right, let's thank all our speakers one more time.